Hello everyone, myself Vaishnav Pawar from Department of Statistics at Patel University. Today we are discussing about principal component analysis from subject computer-oriented statistical method. First of all, what is principal component analysis? Principal component analysis is a statistical method used for dimensionality reduction. It is applied when we have large number of variables in dataset. Many variables may be correlated, which create complexity in analysis. PCA converts these correlated variables into small set of uncorrelated variables. These new variables are called principal components. Each principal component is linear combination of original variables. The first component captures maximum variation in the data. Subsequent component capture remaining variation. This helps simplicity data using losing much information. Principal component analysis is widely used in data science, machine learning, and statistics. Then properties of principal component analysis. If P minus R smaller eigenvalues of sigma are equal, then first we have to choose the first R principal components. This is given by Bartlett, and Bartlett, this is our test statistic with degrees of freedom 1 minus 1 by 2 P minus R plus 2 into P minus R minus 1 degrees of freedom. Uh, Basically, this principal component analysis based on eigenvalues or eigenvectors of the covariance matrix. Eigenvalue represent the amount of variance explained by each component. Larger eigenvalue indicate more important components. Smaller eigenvalue indicate less important components. If some eigenvalues are equal, then their components have similar importance. Bartlett test is used to check equality of smaller eigenvalues. This tells help to determine how many components to retain. The covariance matrix summarizes relationship between the variables. Eigenvalues gives the direction of principal components. Together, eigenvalue and eigenvector form the basis of the principal component analysis. Now, in PCA, we test whether eigenvalues are equal or not using the chi-square test. Our null hypothesis is nothing but selected eigenvalues are equal, and our alternate hypothesis is these selected eigenvalues are not equal. Chi-square test is used for this purpose. If the null hypothesis is rejected, then we have to continue the process. If our null hypothesis is accepted, we have to stop there and we have to take the first R components. Similar components can be removed from the analysis. This reduces the dimensionality of the dataset. This testing is done step by step for different values. It helps in identify the optimal number of components. Now, selection of components. The remaining P minus R component explains the smaller portion. Then we have to choose the first R components. Then we have to take, for verify, we have to take R equal to 0 and taking the arithmetic and geometric mean values. Our goal is to select the principal component explaining the maximum variation. The first few components captures most of the data variability. Remaining components contribute very little. If smaller eigenvalues are equal, those components are less useful. Such components can be ignored. This reduces the number of variables in the model. The selection process involves repeatedly hypothesis testing. We start the smallest eigenvalue and move upward. Once the hypothesis becomes true, we stop and the selected components are used for further analysis. If our chi-square is not accepted, that is chi-square rejected, we have to continue the hypothesis testing and procedure. A naught is our A naught is our arithmetic mean, and G naught is nothing but our geometric mean. Now, first we take R equal to 2, R equal to 0, A equal to, and arithmetic mean and geometric mean, and we put the values in this in test statistic. Then, for first, our null hypothesis is rejected. For r equal to 1, our null hypothesis is rejected. R equal to 2, our null hypothesis is rejected. Up to r equal to 3, our null hypothesis is also rejected. For r equal to 4, we accept our null hypothesis. Then we have to select our first four principal components. These four principal components explains the maximum variation, that is 97.75% of variation of the dataset. Here the decision regarding the number of components can be retained is taken on the basis of the test, but uh, there are other methods to decision for principal components to be selected. There is also others methods to select the principal components. Now, test of lambda from correlation matrix. We have discussed the test of equality of lambda where principal component analysis performed from variance covariance matrix. The analysis performed using correlation matrix as input. In such a case, null hypothesis. A procedure is the same as variance covariance matrix. Our null hypothesis looks like lambda 1 equal to lambda p equal to lambda 2 equal to lambda p. This is our chi-square statistics. Then our degrees of freedom is 1 by 2 p in bracket p minus 1. Here is also we use the LRT test. And then A and A naught and G naught is the arithmetic and geometric means of p minus r smaller eigenvalues of from the correlation matrix. Now also if last p minus r eigenvalues are equal, then we have to choose the first r components. Then we choose the first four components as the principal components. And then these are the principal components divided by total number of components in 200. That is 96.46% of variation explained by the first four components. Also, it is useful to have different units. In case of hypothesis testing, it is applied on correlation matrix. Bartley's test is also used in correlation matrix. If p-value is small, eigenvalues are not equal. This indicates components have meaningful. Correlation matrix provides more reliable results. It is commonly used in real-world application. The principal components obtained from more data vector are affected by a scale and measurement. It is different variables. The amount of variance will not be homogeneous type. Thus, eigenvalue and eigenvector calculated from variance covariance matrix will not be similar found as those found out from correlation matrix. When correlation matrix is free of scale and measurement, this phenomenon is seen in contrasting the components found out. So, variance covariance matrix and correlation matrix. That is the total variance of X is explained by R components in last P minus R eigenvalues are zero. This property is consistent with property 2, that is lambda criterion. Decision regarding the principal components. We have to selecting the number of principal components is our key step. Different methods are available for the selection of principal components. These include statistical states and graphical methods. Eigenvalue also help to make decision making, aims to explain the maximum variation, at the same time reduce number of components. No single method is perfect for that. Combination of method is preferred. Practical judgment is also required. This ensures optimum selection. Now, covariance matrix approach, that is variance covariance matrix as an input. When covariance matrix is used, scale matters. Small eigenvalues indicate less important components. Components with near zero values can be removed. Equal eigenvalues indicate similar components. However, result may sometimes be misleading. Significant components may explain very little variation, so statistical significance is not always sufficient. Interpretation of variance is important. Practical understanding is also required here. There is limitation of this approach. Our null hypothesis is also this, and these are the eigenvalues of the components. Now, the this is formula for the total number of percent of variation explained by the principal components in original data. This is nothing but our principal components. Summation I j equal to 1 to r is nothing but our principal components. Then the summation of principal components divided by total summation of all components in 200. Then we get the total percent of variation of the original data set, and this is given by S. Mardia at 1979. I have mentioned that if this percentage is 90 or more, select those R components. Now, correlation matrix as an input. It is already have been mentioned that test of equality of lambda is a table for lambda is are estimated from correlation matrix. That is the S. Mardia is given. If there are uh, eigenvalues greater than 90, sorry, if the variation explained by the component is 90% or more, then we have to choose the first R components. Also the scree graph dot plotting the eigenvalues in y-axis and corresponding number of components to be selected are equal to number of points above the straight line. Later on, Kettle and Jesper have proposed the similar technique. Now, the scree plot is a graphical method. Eigenvalues are plotted against the component number. These are the eigenvalues and these are the component numbers. The plot shows decreasing trend. Look for the elbow point. This is nothing but our elbow point. Components before elbow, that is the before elbow, are selected, and after elbow, that is this point, we have to remove these points, and that is our eigenvalues are small here. This method is easy to use and no complex calculation needed. However, it is subjected, but sometimes it is interpret differently. Different people interpret differently. It is experimental to experimental. That is nothing but the drawback of scree plot. Effect of ignoring some components. This is the Horn method compares data with random samples. It improves the reliability of selection. Kaiser rule suggests that eigenvalue greater than 1. Joliffe suggests that eigenvalue greater than 0.7. These are alternate selection methods. Each method has its own advantages. Used based on dataset type helps to remove decision accuracy. Combination gives the better results and provide flexibility and analysis. Now, effect of ignoring some component. Removing components simplifies the data, but it may cause the loss of information. If you remove the components all the time, then we lost some information. If we get some information a from every component, but it may be sometimes it may be important information. Each component contains some variation or some information. Components loading shows the importance of the variable. High loading means strong representation. Removing such components are the risky. These are the amount of variation of xi explained by the R components. This is the formula. Then the sample quantity is estimated by GIJ square is nothing but our weights. Uh, Variance covariance matrix is used as an input in principal component analysis. The latter amount of variance of xi is estimated by SSI. If we divide the SSI by the weight matrix, then we get the amount of variance of xi. Large loading is variable strongly. How variable strongly represent that is the component. High loading means the strong representation of the variable. to their component. High loading means high representation. Remove such component is risky. Must analyze before the deleting. Balance between simplicity and accuracy is needed. Keying important components and remove only less information ones. In these components or in this correlation coefficient matrix, the first two components of x1, x3, and x7 explain more than the 90% of variation. Sorry, x2, x4, and x5. X2, x4, and x5 explain the more than the 90% of variation. Then x1, x3, and x7 explains first two components can't explain the above the 90% of variation. So they explain the 81, 89, and 87, 88% of variation by the first two components. But if we add the three components, if you add the three components in these, then we get the 90% explains, expect the x6. Still x6 with three components will not be able to explain the more information or above 90% of variation. So there is chances to, if we are not above the 90% of variation, we will losing some information. If our component explains at least 90% of variation of all variables, we will be losing less information of the all variables. Now, principal component analysis in principal component regression. Principal component analysis used in principal component regression. It solves multicollinearity problem. Multicollinearity means correlated predictors. It affects regression accuracy. Principal component analysis. Variables are uncorrelated components. Regression is performed on these components. After that, it improves the model stability, estimates more precise estimates. This method is also called principal component regression and widely used in practice. This is nothing but our regression model. We know that the expectation of u equal to 0 and expectation of u dash is nothing but variance of u, and it is sigma square in. In is nothing but identity matrix, and this is our least square estimate of beta. If we also know that the rank of x equal to p, this latter condition is violated, that is a determinant of x equal to 0. In this case, our regular inverse is not exist. Then we have to find the generalized inverse, and OLS method to estimate beta also breaks down. This case known the perfect multicollinearity problem. In this case, the multicollinearity is present so that the our determinant of x is not equal to 0, then our regular inverse exists, but it is equal to 0, then our regular inverse is not exist. Then we have to take the transformation, or we have to take the orthogonalization of X matrix and different steps for regression analysis with the orthogonalization matrix to drop out the multicollinearity problem. Now the original variable transforms into components. These components are orthogonal. This is nothing but our orthogonal transformation. We take z equal to gamma dash x and y equal to z gamma dash beta equal to beta plus u, and zb plus u. B is nothing but gamma dash beta. Therefore, the least square estimator of beta is b is z dash z inverse z dash y. We know that the z dash z is nothing but lambda inverse divided by n. Then our b cap is look like this. The b cap is unbiased since expectation of b cap equal to b. Then our b cap is unbiased estimator. Then this is the variance, and v cap follows p variant normal with mean b and variance covariance matrix sigma square divided by capital lambda. And after that, estimator of sigma square is also MSC equal to y dash y minus beta cap z dash y divided by n minus p minus 1. The statistic is for significance is nothing but our null hypothesis is bi equal to 0 and t equal to bi cap divided by standard error of bi cap. We have estimated p vector of parameter from the estimator of original parameter of beta is estimated. where beta cap equal to gamma b cap. This is nothing but our expectation of beta I cap and variance of beta I cap. The sample of beta I cap is obtained by beta I cap equal to summation j equal to 1 to p gij into bi cap bj cap. Gij nothing but our weights, where lambda lj is the jth eigenvalue from the x dash x divided by n matrix. With sample data, gij is ith element of eigenvector corresponding to the eigenvalues lj. Now let's go towards the example. In our example is based on the child mortality and fertility reported by the Booyan. The variables of y, that is our dependent variable, is the number of ever born children. X1 is nothing but social status. X2 is education of father. X3 is the education of mother. X4 is the desired number of children, and the X5 is number of dead children, X6 is the occupation of father, X7 is the occupation of mother, X8 is the duration of marriage, and this is the data. We have eight variables, X1 up to so on X8. These variables are correlated with each other, then there is a multicollinearity is also present, which sense that there is multicollinearity. But we also check using the correlation matrix. The occupation of social status is measured by low, medium, and high. Respectively, the one is low, two is medium, three is high, and education of father is in number of schooling. Occupation of father is zero if labor, one if farmer, two if service, and three if the business, and four if the others. Occupation of mother, x7 equal to 0 if housewife, x7 equal to 1 if farming, x3 equal to 2 if service, and duration of marriage is completed years. Here n equal to 60. The objective of the analysis is to fit the model similar to that. The dependent variable is 5. The number of your born children, the correlation matrix of x is shown below. The x1 and x3 have correlation 0.7. X2 and X3 have 0.720. So multicollinearity exists and there is high correlation between X2 and X3, like that X4 and X5, X5 and X4, also X5 and X8. So multicollinearity is present there. So after that, eigenvalues. Eigenvalues of correlation matrix is nothing but 2.96, 1.91, or 0.95, L4 equal to 0.85, and 0.64 and respectively, or likewise. Larger eigenvalues is most important component. Smaller eigenvalues means less important component. These are the weights of principal component analysis. Each component equal to weight combination of variables. Weight is nothing but our eigenvectors, and it is denoted by Gij. Thus, the first principal component is this is the linear combination of the variables, that is weighted combination of variables. Similarly, it is for one first component, first principal component. Likewise, we have to take this as well, eight components. After that, we have to replacing zj's by the linear combination of xi's. Then we get this, and the coefficient in later fit integration line are beta. The estimated standard error of beta is RESE. These are the estimated standard errors. These are the bias and mean square errors and relative efficiencies formulas. Let us now perform the regression analysis by dropping four components corresponding to eigenvalues. If eigenvalues is less than 0.70, then we drop these components and take the other components, or using the scree plot, we can take those components who explain the 0.70% variation. Then our regression by dropping components on the basis of lambda J criterion. This is the result. It is noted that that what I say, if lambda L is less than 0.70, then we have to drop those components and we have to only select the L greater than 0.70, that is eigenvalue. If eigenvalue is greater than 0.70, then we have to select those components. And this is by t test corresponding to the t test. Here, if p-value is less than 0.05, then those components are significant. First component, fourth component, fifth component, and eighth component are selected using the chi-square, so is using the t-test or p-value corresponding to the t-test. And then here is the result that uh, these four components by the t-test criteria explains 89.16% of variation of the by the explanatory variables on the principal component regression after deleting components using the lambda criterion leads to explain the 84.16% of variation of y by the explanatory variables. After method of discarding components, principal component analysis select those components which can explain 90% variation of the original data set. Each selected principal components is discarded from further analysis. If the that is the our if our compound explain 90% or more than 90% of variation, as the criterion select important variables, the square of multiple correlation coefficient R square is calculated. Delete details of the have been discussed by the Bill in 1967, Bill 1970, and Thompson 1978. In the present section, we discuss the method of regarding the principal component analysis. We have to select those components which lambda less than equal to lambda greater than equal to 70. Then we have to select only those components which are greater than which components have eigenvalues greater than equal to 0, and we have to delete those components that is lambda less than equal to 0.70. We have to drop those components, and also uh, unless the p minus r variables are deleted if they are equal. This is nothing but our by the lambda criterion. If the eigenvalue is less than 0.70, then according to Joliffe and Jeffers, uh, these variables can be deleted. And since the absolute significant, so absolute coefficient is 0.7954 and x1 and x5 is largest, so it can be deleted from the further analysis. In Z6, Z7, and Z6, the largest absolute coefficients are observed from for variable x5, x4, x8 respectively. Therefore, these three variables can also be discarded from the principal component regression. However, x1, x2, x3, and x6 are those selected components. The result is also not satisfactory because the x1, x2, x3, and x6, after discarding variables x4 over x5, x7, only explains 6.5% of variation of one of y. This aids to conclude that the method of discarding variable are discussed not suitable to every dataset. In that case, it is better to follow the method of deleting of variables as given by Joliffe. According to him, the variables are also deleted to be deleted in such a way that the variables or selected component can explain 80% of variation or 80 or more than 80% of variation. Thank you. This is my time. Thanks for hearing me and supporting me. Thank you, everyone. See you.